Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the conference Optimizing Power Supply to an Oil Field. The material of conference was organized by the engineer Jesus Velasquez Bermudez, Ph.D. In a regulated environment, generation, transmission and distribution are operated by a vertically integrated enterprise, usually a state enterprise that has a monopoly for the supply of electricity, whereas, in a deregulated environment, different parts of the electricity grid are owned by different companies, mostly private, and the electricity markets provide a platform that encourages competition and active consumers. Due to the new power technologies, this liberation of the electricity market has reached the industrial factories that must face this new opportunity. To achieve energy efficiency, industries must include in their digital transformation processes the management of energy, and the control of the carbon footprint. This involves two major processes related to advanced analytics. Offline optimization, planning. This stage is related to the optimization processes that must be carried out prior to the commissioning of the redesigned energy system in accordance with modern methodologies of advanced analytics, and available computational power. Part of this stage are the following activities. Redesign the power supply system in accordance with the new power technologies in force and with a vision of the near future, due to the speed of change of such technologies. Presumably when the industrial plant was built, new concepts, such as smart grids, did not exist. Optimize the industrial process using complex modern mathematical models. It is possible that the industrial plant is operating based on outdated mathematical models, which do not take into account the computing power of the current methodologies of advanced, parallel and distributed analytics. Integrating the planning and programming of industrial processes, transformation of matter, with industrial services, transformation of energy, this is a core element in the whole process. The diagram presents what could be an old power supply system. A modern power supply system is impacted by new power technologies and advanced analytics, artificial intelligence, machine learning and large-scale mathematical programming. The second major digital transformation process is related to online optimization, programming. The final part of the process of restructuring an energy system is the so-called demand response, which involves the participation of consumers in energy systems, as a means of optimizing their profits. At this stage you should use an optimization model for the planning and scheduling of the dispatch of the energy system, together with the optimization of production. Use models oriented to the optimal control in real time of the dispatch of the energy system. Energy trading and risk management. This activity is commonly called ETRM. Topic: Overview. The decision support system that is going to be presented will be called OIL, Oil and Electricity Optimization. The conceptualization of the field can be done based on the following principles. Well, it corresponds to the basic unit of production. Reservoir, it corresponds to a set of wells that operate an oil deposit that is interconnected in the subsoil, and field, it corresponds to a set of multiple oil deposits which contribute their production to a collection and processing infrastructure. The collection infrastructure is composed of separator, production unit in which oil, gas and water are separated. Collector, it is composed of a network of pipes that connect the fields with the separator, and tanks, storages of oil, gas and water, already processed. The topologies of the network can be very varied, since an O&G production facility can have multiple components of each type. The image presents the hierarchical connectivity of an oil field infrastructure. A processing system has multiple fields of production. In a production field there may be more than one reservoir. A reservoir is exploited by multiple wells, some for extraction and others for injection. The latter type of wells depend on the technology used to exploit the reservoir. The wells are connected to a collector that conducts the oil to a platform. The platforms can be connected to other platforms, or to a separator plant. The collectors are used for these connections. The separator plants are used to absorb oil on the water, and the gas on the oil. These products are stored in tanks. Oil, to be dispatched to other facilities of the oil chain. Gas, for reuse and injection, or to be dispatched to other facilities of the natural gas chain, and water, for reuse and injection, or to be processed in water treatment plants, for be re-injected into aquifers, or to be incorporated into the surface water flow system. Oil L optimizes the design, or redesign, of the electrical system that meets the demand for electricity, required to produce crude oil in an oil production industrial field, or in a set of oil fields. Decision modeling considers the following alternatives for investment or disinvestment actions in electric, or industrial, infrastructure, installations of the production system. Well-to-bar connectivity, buses. Connecting facilities to bars. Connecting injection control water plants to bars. Connecting renewable energy sources. Assigning transformers to circuits. Assignment of self-generators to bars. Connecting generation units to the mains. Power purchase agreement analysis, and designing the topology of the electricity supply network. Smart grids are the current power technology to efficiently supply electricity, under the new Industry 4.0 revolution. The main characteristics of the new power technologies are distributed generation capacity, provided by the new renewable energy sources. Reconfiguration of grids as electricity demand changes, provided by easy switching of remote equipment, and permanent communications between equipment and industrial asset management centers. The optimal handling of these possibilities can only be done by updated mathematical models, which consider possibilities of operation, which a few years ago were not commercially available. The optimization of the smart grid's network topology must be integrated by the following optimization models. Economic dispatch of the smart grid, optimization of the management of electrical energy in small cities, factories, universities, shopping centers, office buildings, urbanizations. Smart grid unit commitment, optimization of the dispatch of the electrical load in real time, or in the short term. Smart grid configuration, optimizing the network topology, it considers voltage control, configuration of feeders, location or activation or relocation of electrical assets, like transformers, capacitors, and phase balancing. Smart grid design, optimization of the design or redesign of smart grids with modern power technologies. ETRM, electricity trading and risk management, decisions to buy and or sell electricity, in a long, medium and short-term market, one day in advance or the day of dispatch. Topic: Decision Support System for Energy Efficiency in Oil Fields. The decisions supported by the DSS are medium to long-term, and are related to the field optimization and the long-term recovery of oil from the reservoir. The modeling is based on the integration of two mathematical frameworks: investments coordination and operations simulation. Energy supply optimization. Oil L is a decision support system, SSD, that integrates tools to support decisions at its different hierarchical levels. At the strategic level, there are three investment planning models: EXP, STA, and NET. At the tactical level of an operations planning model, dispatch. The decision problems solved by mathematical models are: STA, automate the decision of whether it is convenient to connect a new well to the electricity grid, or if it should be self-generated. NET, automate the decision of whether localized self-generation is convenient in each new well, or in each cluster, or if it is preferable to self-generate centrally, to serve a production area. EXP, strategically plan the development of the electrical power supply, for the additional blocks, and additional industrial infrastructure, in the long term, and dispatch, optimize the dispatch of energy sources. The table summarizes the characteristics of each model. Short-term topology design. Optimally design the topology of the assignment of industrial facilities to the electrical system, ignoring the possibility of reconfiguration of the centralized electrical network, which remains static during the optimization process. These decisions are of a medium-term tactical nature, on the order of 1 year. As a result, the operational configuration to be used throughout the period covered by the planning horizon is determined, since it does not contemplate dynamic infrastructure expansion, because decisions are made at the beginning of the planning horizon. It is performed using a deterministic optimization model that is solved for a mean scenario of the uncertainty dimensions. Long-term topology design. Optimally design the topology of the assignment of industrial facilities to the electrical system, considering the possibility of the reconfiguration of the centralized electrical network, taking as a reference all the possibilities offered by the new power technologies, associated with smart grids, and possible contracts with third-party power suppliers. These decisions are tactical long-term, multi-year. As a result, the expansion plan, configuration and reconfiguration, of the electrical network is obtained throughout the planning horizon, since it contemplates dynamic expansion of infrastructure, due to the decision to rebalance the network, in any period of the planning horizon. It is performed using a stochastic optimization mode, L, that includes scenarios for multiple dimensions of uncertainty and financial risk analysis. Among many, the dimensions of uncertainty may be availability of renewable energy sources, prices in the electricity market, prices in the oil market, and oil field productivity. Dispatch of energy sources. Optimize the dispatch of energy sources in the short term. During the run of this model, the entire topology of the electrical system remains static. It is performed using a deterministic optimization model that is solved for a mean scenario of the uncertainty dimensions. The diagram shows the connectivity of the proposed models. Due to their functionality, the models can be grouped into auxiliary models, provide the data required by energy efficiency optimization models. Electrical network design, designs, under different hypotheses, the oil field electricity supply network. Electrical network operations planning, produces the objectives of the energy dispatch operation plan. Topic: Conceptualization of the electrical petroleum system. The flexibility in the supply of energy, mainly electricity, to an oil field, confronts companies in the sector with an environment complementary to that of traditional industrial operations. The biggest changes arise in the supply of electricity, which has evolved with great speed in the last 30 years. Starting with isolated fields, where electricity was supplied by electrogene, to fully modern fields that take advantage of smart grids, electricity purchase contracts, and the liberalization of electricity markets. The technical economic viability of energy storage, coupled with the proliferation of energy technologies based on renewable energy sources, has changed the landscape of the industrial sector, since it is now possible, and increasingly efficient, to generate renewable energy and store it for use in due time. In practice, all industrial companies can be agents that interact in the electricity market, acting as cogenerators and carry out commercial activities and transactions. This, together with the industrial Internet of Things, increases the pathways to achieve industrial energy efficiency. Industrial energy efficiency results of the integration of production processes, transformation of matter, with industrial energy services, energy transformation, aimed at the simultaneous optimization of both industrial production and energy conversion. These processes are related to polluting emissions of gases and liquids, associated with increasingly demanding environmental control laws. The decision support systems may integrate complex industrial process models, in which it is necessary to redesign the power supply system, according to the new power technologies. Additionally, it should be considered that modern electricity markets allow industries to co-generate energy, in such a way as to carry out purchase-sale exchanges, according to the convenience for the two types of agents, buyers and sellers. Either role can be assumed by an industrial producer. The optimal design of oil supply networks linked to electricity supply networks should follow the general principles of modeling such supply chain design and/or redesign problems. It is required to join three types of models: investment logistics and financial risks management, financial simulation following assets and liabilities management methodologies, and Operations simulation to evaluate the future cost of the production activities. Normally, the model of operations must be based on stochastic optimization, in such a way to evaluate the costs and future impacts, due to the uncertainty of the environment of the productive system. In this case, and in general in the industrial sector, it is necessary to link the production model with the electricity supply model. In this conference is made in phases in the modeling of the oil system, and its link with the electric model. To learn more about the management of the electricity sector, interested parties are invited to watch other conferences specializing in the subject. Oil production system. The oil production model corresponds to an oil field modeled in aggregate, without detail of many characteristics, for example, the hydraulic behavior of each well, which allows to estimate the movements of matter and the consumption of electrical energy. The components of the oil production system are, in parentheses the indices used. Oil block, index SB, set of fields that make up the zone region delivered to the producing company for exploitation. Field, index CP, set of clusters that can share production facilities. Well, index PZ, oil and water production entities. The wells are connected to an electric power distribution substation, bar or bus, from which the electricity demand of the well is met. Cluster, index CL, spatial division of the field where the wells are located, every well must belong to a cluster. Control water plant, CWP, index PD, it is a set of pumps that inject the water that is separated from the crude oil. Water is injected into wells that were drilled specifically for that function, or into wells that were thought to be producing, but were not successful from an oil production standpoint. The CWPs are connected to an electrical power distribution substation, from which the electricity demand of the CWP is met. Central Production Facility, CPF, Index FP, oil separation, treatment, storage and transfer, or transport entities that serve a set of clusters. The CFPs are connected to an electrical power distribution substation from which the electricity demand of the CFP is met. A CPF provides production services to a predefined set of clusters. Locative installation, index low, auxiliary support entities of the operation represent offices, camps, military bases, schools, hospitals and other similar facilities. The locative installations are connected to an electrical energy distribution substation, from which the electricity demand of the locative installation is met. Generation unit, index G, installation that provides electrical energy. Two types of generation plants are considered, local generation units, and central generation units. Central generation units consume crude oil, natural and/or diesel. Independent power plant, IPP, index PP, it corresponds to a group of medium capacity generators, typically 6 to 20 megawatts, that feed part of the centralized load. They are recognized as having, by contract, a minimal power availability, called take or pay. The diagram presents the balance of materials in an oil field, which produces oil and water. The water is re-injected into the reservoir. In order to operate the production system requires as inputs energy and injected water, which is produced by the same reservoir. This is a modeling hypothesis. With proper processing, the power generation unit can use part of the extracted oil. Surplus oil and water are exported outside the oil production system. The image presents an example of the possible connectivity between the oil production system and the electricity system. The image presents an example of the possible connectivity between the oil production system and the electricity system. The calculation of the energy demand of a well is obtained from the production of fluids extracted from the well, since fluid production is an input parameter for the model, and that operating conditions are given and constant over the planning period. Energy demand, in turn, becomes a calculated parameter. Within the modeling, it is possible to differentiate the energy consumption associated with the production of crude oil from the consumption associated with the management of the associated water production. For this, the calculation relationships that will be presented in the following, and the proportion measurements that establish the corresponding volumes of each fluid in the mixture are used. The water produced together with the oil must be separated for later re-injection into the reservoir. The proportion of produced water associated with oil production is BSW, base sediment and water. The form of the BSW function is not known a priori, but it can be established by field data and/or reservoir simulations. It should be noted that from the point of view of mathematical modeling, BSW corresponds to a random parameter that is not known with certainty, and that in the long term determines the financial risks to which industrial infrastructure investment decisions are exposed. The graph presents three scenarios for BSW function: pessimistic, medium, and optimistic. This variability can be included in a stochastic optimization model as an uncertainty dimension. The following hypotheses are made with respect to product handling. First, two possibilities are assumed for the management of the crude oil produced: all the crude extracted is delivered for commercialization, and for the disposal of the produced water, it is assumed that all the water is reinjected. Second, to determine the flows of matter, these must be linked to the industrial facilities of the oil field, that is, to the CPFs while loss CWPs. For the above, the following rules are assumed. Each cluster is linked to a CPF, therefore the material processed in a CPF is the sum of the material that reaches the CPF from all the clusters associated with that CPF, and each CWP is linked to a CPF. One CPF can be served by multiple CWPs. Third, since one CPF can serve several CWPs, treated water management is based on minimizing the cost of injected water plus water disposed of in irrigation districts. This implies that the model decides, when there are degrees of freedom, the management of treated water. Alternatively, rules for the distribution of treated water can be established. Below are some of the algebraic equations of the petroleum model. It is considered a stochastic formulation, where EO is the index used for random scenarios. The production of the PZ well for each period of the planning horizon is described based on two basic parameters: maximum average total fluid production in barrels per day, MTPDT/PZ, and percentage of water contained in fluids, BSWT/PZ. These parameters are read from the information system, and from them all calculations of oil production and electricity consumption in the oil system are made. It should be noted that the first parameter can change by the maximum oil production, MOPT, PZ, depending on what is the basis of oil production of each well, FBSWT/PZ. As the parameter BSWT/PZ is not known precisely, it must consider different random scenarios for this parameter. It is proposed to associate it with an index related to the oil production scenario, IBSWEO, in such a way as to be able to represent its variability. IBSWEO represents the relationship of the BSW for the basic production scenario with respect to the BSW of the EO scenario, which is assumed constant for all wells in the oil system. Based on the above, oil and water production, for the EO production scenario, are calculated. The system of equations indicates that the total fluid production is divided into oil and water, considering the factor FBSWT/PZ/EO. The variables, in barrels per day, BPD, used are barrels of oil per day T/PZ/EO, barrels of crude oil produced per day in the PZ well during period T, BWPDT/PZ/EO, water barrels produced per day in the PZ well during period T, and BTPDT/PZ/EO, total barrels produced per day in the PZ well during period T. The production variables, dependent on the production scenario EO, barrels of oil per day, BWPD and BTPD. They are determined by the model considering electricity supply constraints, as it may not be feasible to extract all potentially extractable oil. These variables are calculated considering the levels of planned oil production. MOP/TPZ is the parameter that defines the oil production target set for the PZ well during period T. And DOPE/TPZ/EO is the variable that defines the deferred production, unextracted oil, at the well PZ if the EO production scenario occurs. The total production in a cluster is calculated as the sum of the production of oil and gas in all the wells of the cluster. The variables used are Vocal TCL/EO, barrels of crude oil produced per day in cluster CL during period T, and BWCL/TCL/EO, barrels of water produced per day in cluster CL during period T. The total production in a field is calculated as the sum of the production of oil and gas in all the clusters of the field. The variables used are BO CPT CPEO, barrels of crude oil produced per day in the CP oil field during period T, and BW CPT CPEO, water barrels produced per day in the CP oil field during period T. The balance equations in Central Production Facility, CPF, indicate that the production in the is equal to the sum of the production in all clusters connected to that CPF, and the water injected must be equal to the water produced. This is a modeling hypothesis that can be adjusted for each specific case. The decision variables are WTPDEO, water for injection into the CWPPD, BO CFTFC, oil production, BOCT, FC, in CPFFC, and BWCFTFC, water production in CPFFC. The above variables must be associated with index of consumption of electrical energy, according to the volumes of material handled. The values for the indexes depend on the oil fields, to which the facilities belong. These indices, or productivity factors, are measured in kilowatt-hours per barrel. The energy indexes required are per barrel of fluid extracted, per barrel of crude oil treated, per barrel of treated water, per barrel of water injected, and per barrel of irrigated water. In more detailed modeling, indexes may be associated with the specific equipment used in the industrial process. The energy consumption in a well, as a result of the extraction process, is calculated as the number of days in the period, multiplied by the energy index, associated with oil and water production, multiplied by the amount of material extracted from the reservoir at the well. The energy consumption in a central production facilities, CPF, as a result of the crude oil and water treatment process, is calculated as the amount of water processed, multiplied by the treated water index, plus the amount of processed oil, multiplied by the treated oil index. The energy consumption in a control water plant, CWP, is the result of the sum of the energy consumption in water injection using the CWP. Energy consumption in the CV locative installation is a fixed charge independent of oil production. And the random scenario. Topic: Mathematical modeling of electrical system. In a general model for the electrical sector, electrical connectivity is carried out through a network of circuits and bars that integrates different types of installations, power plants, like hydroelectric, thermoelectric, coal, wind, solar, biomass, places of demand, like industrial, cities, regional interconnections and energy storages. The simulation of the operation of an electrical system, which supplies an oil production field, is similar to the simulation of a high-voltage electrical system, which supplies a wholesale electricity market. The fundamental difference will be the voltage level of the grid, and the industrial assets that are connected to the bars, the substations. On the other hand, the modeling of the smart grids must be considered. This complicates the modeling of real cases, due to the great flexibility in the operation currently provided by power technologies. The professional interested in delving into this topic is invited to see the conferences related to modeling of electrical systems and industrial energy efficiency. From the point of view of money flows, the following should be considered. Oil field operations and oil process installations must be net consumers of energy. Net consumption can be decreased if energy solar installations that can help production at wells are considered. An industrial utility plant that produces energy for oil extraction and processing operations should be considered. The energy balance between the two systems may be zero. However, when there is an imbalance, negative or positive, the differential may be traded in the electricity market. It is also possible to balance using an energy storage. Direct transactions with the electricity market may be carried out through supply contracts with electricity marketers, or by buying energy in the spot market. This activity requires risk hedging modeling, and it is known as ETRM, Energy trading and risk management. The electrical model corresponds to an electricity generation system interconnected, through a distribution system, that allows the electrical flow between the generating plants and the production facilities, where electricity is demanded. The components of the electrical system are: generation units, Index G, generation facility that provides energy. Two types of generation plants are considered: local generators, electrogens, and general generation units, thermal generation plants. The dispatch of these units is carried out by the operator. Each generation unit may have its own contracting conditions. Fuel located, Index K, fuel located at a certain consumption site. Its characterization includes the type of fuel, ACPM, crude oil, natural gas, energy wealth of the fuel, and transportation and supply costs. A generation unit may consume multiple types of fuels. The fuel to be used will be selected by the optimization model, considering its cost and availability. Power supply contracts, Index CS, power purchase agreements, PPAs. Commercial interconnections, Index Z, are related to regional electricity grids entry points. This commercial interconnection is characterized by a price of exchange, a maximum amount to be purchased, or sold, and a transaction cost, that may be divided between the two parties. Operating costs are discriminated into the following costs: fuels, PPA contracts, energy exchange with the regional interconnection system, administration and maintenance, and cost of oil production loss, deferred. The opening of electricity markets, which occurred at the end of the last century, together with the evolution of power technologies, have completely changed the vision of energy that companies must have. This change allows industrial demand to go from being a passive actor to being an active actor that can act in the electricity market by proposing businesses and adjusting its demand to what is most convenient for it. This new behavior is or has been called the demand response. But, like any opportunity, capturing the benefit of this new environment implies the necessary evolution towards learning to act in new markets. For this, many companies have developed new departments, specialized in understanding the electricity market, in order to actively participate in this market. This has given way to what has been called ETRM, Energy Trading and Risk Management. Modeling the price in the electricity markets is not an easy task. This is due to: until now, electricity is a good that has not been storable in its form of consumption. This implies that permanently the generation and demand of electricity must match. This situation is changing due to equipment that can store electricity, such as industrial batteries. The above situation translates into the marginal cost of electricity generation. It varies at the same rhythm as the demand, that is, in real time. This generates volatility and seasonality in the price. Additionally, the abundance of renewable energy sources affects the ability to estimate marginal generation costs, since the composition of generation units required to match the demand changes as the availability of renewable energy sources changes. The forms of future trading of electricity have been developed to reduce the risks associated with price volatility. Depending on the market, there are standardized markets for electricity derivatives, and negotiations through bilateral contracts. All the above, and other additional considerations, make forecasting electricity prices a professional work that requires highly efficient predictive mathematical models. The chart shows the daily spot prices in the European electricity markets during the period between the first day of June 2022 and July 17, 2022. In this case, weekly seasonalities are observed according to the days of the week. Low prices should be associated with weekends, and high to normal business days. Each market has its own behavior. The chart shows the daily spot prices in a U.S. electricity market during February 2001. The information has been organized to observe the hourly variability of the price of electricity. As you can see, the price presents an intraday volatility due to changes in the demand level throughout the day. These expected variations in the level of prices are translated, in one way or another, into electricity supply contracts. This is because the trader always has the spot market as a reference market. If it is considered that the energy consumption of an industrial process occurs throughout the day, if there are slacks, it is possible to determine the best form of production, minimizing the cost of energy, without affecting the level of production. It should be noted that under these conditions, minimizing the cost of energy versus minimizing the energy consumed produces different patterns of daily operation. Only if the company has a flat electricity rate, the same for all hours of the day, the operating patterns will equals. In the example, it is possible to divide load duration curve in 3 blocks: peak, intermediate, and base. The hourly blocks are supposed to have a representative duration of this condition lasts, and it must be guaranteed that the amount of energy consumed under the 2 curves is equal. La duración de los bloques no tiene que ser una variable entera. There are other alternatives to model the blocks, such as piecewise linear approximation. The results of the operation will be distributed in hours, or in hourly blocks, differentiating the price of energy for each subperiod of the period being modeled. Hereinafter, subscripts B will be used to identify the hourly block. Generation costs. It is related to the expenditures derived from the costs of fuels used in thermal generation. For each generation unit G, they are expressed as the sum of maintenance and operating costs, calculated based on electricity generation, and cost of fuel used. The decision variables are GTE/TGB, electricity generation in the generation unit G during period T during block B, and CCO/TGKB, fuel K consumption in generation unit G during block B. Cost of commercial exchanges. It is related to the expenditures derived from commercial exchanges with a regional electricity system. The fundamental variable are TZB, net energy imports from the regional market, purchases minus sales. The cost of the interconnection, in dollars per gigawatt hour, are PICO TZB commercial interconnection reference price, in this case corresponds to the spot price of the wholesale electricity market, in the load block B, plus additional charges for delivery to the bar Z. CTRA/TZ interconnection transaction cost. In two-way transactions, buy or sell, this cost must be strictly greater than 0, to avoid degeneration of the mathematical problem. Degeneration involves an infinite number of optimal solutions, which complicates the solution of the problem, increasing the solution time.